All right, welcome back to ME352, and we are now doing G. Let's see, I have to choose a color here. GM1b, following GM1a. We start with section 1.8, which is equivalent linkages. These are useful where you have higher pairs and for instantaneous analysis. Okay, so we'll start with figure 1.26, which is easy to understand. So we will have something like this, touching something like this. Now that's a higher pair, right? So, but what we will do is we will say, take the local radius of curvature and find the center of that circle. Same on this side, local radius of curvature, find the center of that circle. Let this point be A, let this point be B. Think of point A as being fixed in this body, right? So now here, this was 1, 1, this is body 2, this is body 3. This is a 3-body planar linkage, but with a higher pair here. But now what we are doing is we are looking for an equivalent linkage, and what we have here is A is the center of the instantaneous circle at the contact point. So we'll put a link here. Then we have another link from here to here. Then we have another link from here to here. The claim is that this one is equivalent. Now, why is it equivalent? That is what we need to understand. So the reason is that after a small amount of motion, let us say the contact point from here moves to this point on the body, and the contact point, due to some slip or whatever on this body, it is over here. This distance and this distance, right? So over here, imagine I'm drawing a bigger version. So from this center, this was the old contact point, this is the new contact point. But because locally I have fitted a circle, this distance r and this distance r are the same. So wherever the contact may be, with some slip or without some slip, due to some small change in configuration, the distance between point A and point B will not change. And so it will be just like this, 3 links, and then of course the ground link, which is fixed. Okay, so that's an equivalent link. Let's do a more complicated example. This one has to do with a cam and a follower. And in fact, the use of equivalent links is powerful for cams. So here we have a simple cam follower system. You will see others like this. So this is it's a flat-faced cam follower. Here's the cam. That's the contact point. Now over here I have a local radius. That center is here, let us say. On this body, don't worry about that prismatic joint. You worry about this body and this higher pair. That radius of curvature is infinite, and so over here to infinity. You remember over here, let us say this is A and that point B is at infinity. The point B is attached to what? It is attached to this body here. As this body moves up and down, that point B moves up and down. It does not make any big sideways movements, right? So that point B is always up and down. There's an infinitely long rod. What does this point do? It has to maintain the same distance with that, right? So relative to this follower, all it does is move sideways. And for this reason, the equivalent linkage, I will just draw it on here itself, is a slider here in a slot. From here, this point A being fixed in this cam, that means its distance is fixed. This slider moves in a slot because its relative motion to that one is horizontal. As this one moves up, the slot also moves up because the relative motion is horizontal. That means the follower is extended like this. Okay, and so the equivalent system that's the equivalent system. Okay. If you look at figure 128, 1.28, that's a more complex case which I am skipping because it is difficult to compute. Now let us look at a slightly more difficult example. This example, I will cut off some space here and show you the example like this. So there is this is figure 129, 1.29. So you see this one touches this one. This is one body. This is being moved. As we have already discussed, 4-bar mechanisms have a single degree of freedom. If you think of this as 1, 1 fixed, 2, 3 and 4, you see that is a 4-bar mechanism. Here is a higher pair. We want to do the equivalent linkage. Now when we are doing the equivalent linkage, what do we do? Again the same game. What we come to this body and then we look at its local radius of curvature. We draw the center of the circle, which is here. Okay, so this point attached to this body and another point attached to this rod, that is what we are going to use. Now where is the point attached to that rod? Because this is flat, that point perpendicular to the rod but at infinity. This is A, that is B, but it has gone off to infinity. Okay, now that point at infinity is attached to this rod and this is an infinitely long rod. Now this is going to be connected from A to B. B is attached to the rod. Even if the rod turns, it doesn't matter. B moves wherever it has to with the rod. And then the travel of A is going to be perpendicular to the rod AB and therefore it will be like this, parallel to this face. And therefore the equivalent linkage is going to be, now I'm going to try to reproduce it here in yellow so that it is a little clearer. This, so if this point, this one corresponds to this one This one corresponds to this one. Over here, this link I will draw like that. This link I will draw like that. This one attached to ground. This one attached to ground. This was being driven. This part, this link here is here. However, this point A is attached to this link, so I will come here. From here I will attach point A, rigidly attached like this. Over here is a slider which is parallel to this rod, so that rod happens to be there. Sorry, let's clean that up a bit. So that's where that rod is. And attached to that rod is this extension. In that extension there is a slot parallel to that rod. There is a slider. That is attached here. So with a different color, let me emphasize, maybe with blue, this part, and this slot, they are one body. They are one body. This link, let me show that with red. This link is this link here. This link is this link here. This link is this link here. This point A, which was based on the circle over there, that point here is A, which is rigidly attached to this link. This slider moves in this slot. So this is an equivalent linkage. It is good for infinitesimal analysis up to acceleration. Okay, so that takes care of equivalent linkages. Now we are going to look at 4-link planar mechanisms. This is section 1.9. We are going to look at lower pairs only, which for us revolute and prismatic. Now these 4 links have to be connected in some way. They can all be revolute. We will call that 4R or R, 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 R. And that is very simple. That we have seen repeatedly already. That is this familiar 4-bar linkage. We can fix any one of them, and when we do, we can see that it has a single degree of freedom. When we move this link must follow the arc of a circle. Wherever we move it, it goes there, and then if we say this distance is L0, then from here there must be L0. This distance is L1, from here it must be L1. What we can do is we can draw another arc like that. From there we draw this arc with radius L1. Then from wherever this one has gone, we can take a compass with length L0 and cut an arc here. That is the new configuration. So you can see it has 1 degree of freedom. If we assign this angle, then the rest of the positions are determined. Okay, so that's 4R. 3R1P. That means there is one prismatic joint. Let us see what the schematic is like. These figures are in your book. I am drawing them just to give you some discussion. Okay, so you see that's your 3R1P. If you want to understand whether in fact it has 1 degree of freedom or not, I think it is good practice to do that. What we will do is we will think of this link being held fixed, and then we will come here and think of this link being moved. So because it can only slide along like this and this angle does not change, so let us say it comes here. Okay, so now I know where this point has come. After I know where this point has come, this length, and over here this length, arc of a circle, this point I know, I take this length, I cut an arc with this radius, I have located this point, everything is located, and you can see 1 degree of freedom. Okay, so that is 3R1P. If there are 2 R's and 2 P's, then it's a little more interesting, because if I have 2 R's and 2 P's, then I can have R, R, P, P, or I can have R, P, R, P. And these are different. Some examples are there, we will see them later, but for the moment, let us just say R, R, P, P. Excuse me. So what is R, R, P, P? This again is given in your book. I'm just drawing the figure here for you to see how it fits. It's interesting to bend it to some other direction to match this direction here. Okay, so that is RRPP. Now, does it have 1 degree of freedom? We think it does, but let's look at it intuitively. So what we will do is we will fix this one first. Then we can think of moving this one. When we move this one, all it can do is come sideways. This can go like that. All right, and all this point can do, because it's on this circle, it can only move on the arc of a circle. All right, and then it has to, this angle has not changed. See, this angle has not changed, and since this slider is on that rod, therefore this angle has not changed. It can only go up or down. And what is the criterion it will use? As this has moved to the left, this needs to move a bit to the left. We have to find a point here such that the distance parallel to this line over here is the same as the distance here, right? So then we will find that location. It will move just enough along this arc so that the length of this rod here remains the same. Okay, so you can see that it has 1 degree of freedom. That's how RRPP works. How about RPRP? The schematic for that is here. By the way, don't be confused about the finite lengths of these lines. These lines are as long as they need to be. When we say prismatic joint, it can go as far as we want. So once again, this is the R, this is the P, this is the R, this is the P, okay, R, R, P, P. Here is the linkage. Now, how do we know that it has 1 degree of freedom? I think it is worth looking at. Let's look at it like this. Let us think of fixing this link. Now, on this link, when I move this one, it can only move like this. This angle stays the same, that height stays the same. Okay. So this hinge point just moves here. All right. Now, how about this one? This one rotates, right? So suppose, let us imagine, let's see now. Let us imagine that this one comes a bit forward, more horizontal. That's not going to work. Suppose it goes a bit higher. How will it work? So this point, let us say it goes this way, moves in an arc, right? But when it comes here, this angle is going to be a little bit like this. So this line can't go through. Similarly, when it comes here, this angle is going to be a little more like that. And when it is a little higher, then this one will go through. I hope it is clear. Let me try to say it more clearly. When it was in the original position, this line was reaching here. Now it has come here, so it is at a slightly higher position. Therefore, its elevation is bigger. This will move to the left. This position will take that 1 degree of freedom again. At least intuitively, you can see that it will work. It may be a little harder to imagine, but if you spend some time thinking about it, you can see how it will work and how we are going to do that. How we are going to do that degree of freedom calculation is, of course, calculating it requires equations that we are not writing at this time. Okay, now let us talk about mobility and range of movement. So let's come here. Now let's begin here. Let's begin here. But at this time here, this is 110, mobility and range of movement. We are doing the mobility part first. Okay, so we are interested in the number of degrees of freedom of a mechanism. In particular, we often want the number of degrees of freedom to be 1. That means that if we specify the location, if we fix one link and we specify the location of one other link, all other links should be known. Okay, so their locations must be known. So we'll start with something very simple called the Kurzbach, unless it is Kurzbach equation. And what the Kurzbach equation does is it says we are interested in planar linkages with simple hinges. So let me explain what is not simple. Suppose I have a link like this. Sorry. Suppose I have this linkage. This hinge is a problem, right? Because it connects one body here, one body here, one body here. It actually connects 3 bodies. And what we will do is we will draw this instead like that. So we will think of it like this. Okay, so this will be one body, and then this is a hinge between two bodies, this is a hinge between two bodies, and over here this is a hinge between two bodies. Okay, so then those are simple joints. We also allow prismatic joints because prismatic joints and simple hinges both have the following property. If I have one body in planar motion, it has 3 degrees of freedom, right? 2 in translation, 1 in rotation. I have another body that also has 3 degrees of freedom, but when I join it with a hinge, what happens is at that point in this body, this degree of freedom and this degree of freedom got taken away and only one rotary degree of freedom remained, and so 2 degrees of freedom were removed. Okay, now when you take a prismatic body, something very similar happens. Suppose I have this link which is fixed, on that I have a slider. What can this slider do? It can only move in this direction. That means it has 1 degree of freedom left, 2 degrees of freedom are removed. Okay, so for such lower pairs, what we can write is this: the number of degrees of freedom is equal to 3 times n minus 1. N is the number of links, one is held fixed, all the others have 3 degrees of freedom, minus 2 times j, where j is the number of simple joints. Okay, each joint removes 2 degrees of freedom. So that's your Kurzbach equation. Remember, we are also interested in a special case, which is f equals 1. So we write 1 is equal to 3n minus 3 minus 2j, or 2j is equal to 3n minus 4. We will be using this equation soon. Okay, I think in the next video. All right. Good. Here's what happens. 3R1P. Remember, we satisfied ourselves that it was 1 degree of freedom. Well, n equals 4, j equals 4, f equals 3, 4 minus 1 minus 2 times 4. That is equal to 9 minus 8 equals 1. Right? That's how it works. Now, what happens when there's a higher pair? So we were looking earlier at this problem. One link here, another link here, another link here, round body, and a follower here. So this is a higher pair. What is that contact, right? So now in this one, what are the bodies? How many? So there is 1, 2, 3, 4, and 5, right? So 5 bodies. 3 times 5 minus 1. How many pin joints are there? How many lower pairs are there? 1, 2, 3, 4, 5. So minus 2 times 5. But the higher pair actually has a sliding degree of freedom and a rolling degree of freedom. The higher pair has 2 degrees of freedom, so it removes 1 degree of freedom. So minus the number of higher pairs, which is 1. Let us see how that works. That is 12 minus 10 minus 1 equals 1. Okay, so that's correct. 1 degree of freedom for that mechanism. Okay, higher pairs. Now sometimes we have redundant degrees of freedom. Okay, so what's a redundant degree of freedom? Look at this problem. You see this rod over here can move without affecting anything else. So that's a degree of freedom, but it's a redundant degree of freedom. As it happens, if I change the shape of the rod from straight, then the redundancy disappears. Okay, so if I think of the rod like this, now it is no longer redundant. What is the formula for this? 1, 2, 3, 4. The number of bodies is 4. F is equal to 3, 4 minus 1. How many joints? 1, 2, 3, 4. Minus 4 times 2. 2 times 4. I should write 2 times 4. Okay, so that's 9 minus 8 equals 1. It is 1 degree of freedom, happens to be a redundant degree of freedom. This one, also 1 degree of freedom, but not redundant. Why is it not redundant? Because if I try to slide this one out, then it will come like this, right? You see, and that's not possible. So you can see that you can't just move one of them without moving any of the others. This formula remains correct. F equals 3 n minus 1 minus 2j minus h. Okay, but if we have redundant degrees of freedom, then we may wish to write it like this. Then we say F effective is equal to 3 times n minus 1 minus 2j minus F redundant. These are redundant degrees of freedom. Here's another example of a redundant degree of freedom. I have this cam. I have a follower which is perfect circular roller. And what happens is, this is the higher pair, right? What is the number of degrees of freedom? If you look at the number of degrees of freedom, so this is 1, that's 2, that's 3, that's 4. Number of bodies is 4. F is equal to 3 times 4 minus 1 minus the number of joints. 1, 2, 3. So minus 2 times 3 and 1 higher pair. Minus 1. So this is equal to 9 minus 6 minus 1 is equal to 2. It seems like it has 2 degrees of freedom. However, one of those is a redundant degree of freedom. This wheel can be rotated about this axis and nothing else moves. Okay, so if I remove that, then it will, by this formula, this will have 1 effective degree of freedom, and therefore it isn't a useful mechanism for us. It is a constrained, it has constrained motion. Okay, sometimes we may have bodies that are redundant, we may have links that are redundant. So let me give you an example. It's all there in the book, but here's a redundant link. In this one, So you can see that this is the parallelogram, right? I mean, it's perfect parallelogram. But over here, I can add another link. And this link is redundant. It's a redundant link. In fact, if I keep this, then I can remove this link and it's just the same. The motion will be the same. So if I have redundant links, NR in number, then F effective is equal to 3 times N minus NR minus 1 minus 2J minus H minus FR. There is also an example of a redundant joint, and this I will ask you to read the book, and the system that is given, the example is 1.37E. Okay, that takes care of that. There were some now what we will do is we will do the minimum number of binary links in a constrained mechanism with simple hinges. Okay, and this is sort of interesting. We are continuing with number synthesis. Okay, you will notice it is unexpected. Pay attention, it's sort of clever. It seems easy, but somehow minimum number of binary links in a constrained mechanism. What's a constrained mechanism? F equals 1 with simple hinges. Now, this is interesting. Remember this problem. So I have as an example, we did this problem and we agreed that it is 1 degree of freedom. Okay, this is a ternary link. This 1 is a ternary link. How many binary links are there? 1, 2, 3, 4. Is it possible to have links with more than 4 binary links? See, mechanisms with more than 4 binary links, yet F equals 1? That's a question. When we are looking at questions like this, we are trying to understand how many different types of mechanisms can be formed, which are relatively simple, but they sort of help us understand the constraints that we must work under or the possibilities that we have. Okay, so what is the minimum number? And the way we do this is we say that every joint, see, so we will say let N2 be the number of binary links. Let N3 be the number of ternary links. Let N4 be the number of quaternary links. Okay, and so on. Now, N is equal to N2 plus N3 plus N4 plus up to Ni, which is whatever the highest number is for the link. Okay. Now there is another thing that we are noticing is that every hinge or every joint, every simple hinge actually involves parts on two links, on two sides, right? So for example, suppose I have this link with a pin Then over here there is this link which has a hole in it, right? So this one will fit here, right? So there are two elements. This is one element, this is another element, right? So each hinge has two elements, one per link. Okay, good. Now, here is the interesting part. Let me see where my space. Okay, all right. Now, the total number of elements is equal to 2j. But the total number of elements is also equal to 2n2 plus 3n3 plus 4n4 plus I n I, right? Because the binary link has two hinges and each hinge has one element on the link. So there are two of them. A ternary link has three hinges. So there are three elements. Okay. Now we also have the Kutzbach criteria, right? Sorry, yeah, the 2j minus 3n plus 4. We will come to that. Let me just arrange these. So here and here we have our answer. So we have, let's see now. Let's see now. We have 2j minus 3n plus 4 equals 0 because we have a planar linkage and we have a single degree of freedom. 2j is E is this here, and so we have 2n2 plus 3n3 plus 4n4 plus I mean plus dot dot dot, okay, minus 3, and what is n? N is the total number of links, right? So n is n2 plus n3 plus n4 and so on. So minus 3 n2 plus n3 plus n4 plus ni plus 4 is equal to 0. And here is the cool thing that happens. 3 and 3 and this 3 and 3 cancel out. So we are not interested. This minus 3n2 and this 2n2 gives me an n2 on the right hand side, but I'm going to write it here. n2 equals, and then what do I get? I get 4n4 minus 3n4. That means n4 plus I get 5n5 minus 3n5. So 2n5 plus, right? And then plus I minus 3 n I plus 4 is n2. Okay, so now you see each of these, I is obviously bigger than 3, right? So this is a non-negative number, this is a non-negative number, they are all non-negative numbers, and 4. Therefore, n2 is greater than equal to 4. Even if you have ternary, quaternary links and so on, if your linkage has 1 degree of freedom, then the number of binary links in it is at least 4. So this, to me at least, was a surprising result, and we will stop here.